So today we'll be looking into the transmission losses. We have seen in the previous classes uh, wherein we had discussed about ARP, okay, which is nothing but the equivalent isotropic radiated power, and we saw the associated formulas and the gain factor, and we also saw a few examples and another type of example in which we can actually find out the gain of the antenna. So today we'll be looking into transmission losses, okay, and the EIRP may be thought of as a power input to one end of the transmission link, and the problem is to find the power received at the other end. So as you have seen in the previous classes, the power in is not equal to the power out, right? So this losses can happen due to the feeder, due to the lines which are connected, and due to this, what is going to happen is you are going to face something called loss. So this is the reason why we find your P in is not equal to P out. Okay. Other losses can be estimated from statistical data, and some of these are dependent on weather conditions, especially on rainfall. So as we have seen extensively, attenuation which is caused due to rain is one of the major factors, right? Because of the ice, because of the water molecules. So these signals can be diffracted. So once these signals are diffracted, then there's no option or of these signals traveling down to the base station. So which means the percentage of reception is going to be very less. The first step in calculations is to determine the losses of clear weather or clear sky conditions. So first you have to find out what is your ideal conditions. These calculations are taken into account the losses, including those calculated on a statistical basis, which do not vary significantly with time, right? Okay, so losses which are weather related and other losses which fluctuate with time are then allowed for by introducing appropriate fade margins into the transmission equation. So what is a fade margin? The amount that you can actually, uh, the amount of fading of a signal that is permissible. So which means even if it fades to a certain extent, it should be fine. Okay, so even though it's a degraded signal, it should be fine. So we try to define fade margins. So our communication signal should be greater than these losses. Then we look into the free space transmission. Okay, so here as a first step in loss calculations, the power loss resulting from spreading of the signal in space must be determined. This calculation is similar to the uplink and downlink of the satellite circuit. So which means just like how we calculate the uplink and the downlink, in the same way this free space transmission is also calculated. So for this we have something called psi m, okay, which is equal to EIRP divided by 4 pi r square. So EIRP, again you have to get back to our previous equations, okay, wherein it is equal to your PS plus G, okay. Sometimes it's also referred to as G into PS. Right. So yeah, so we have this flux density, okay, the power flux density, and which is equal to ARP divided by 4 pi r square. A fundamental relationship exists between the power gain of an antenna and its effective aperture. Okay, so this is the gain. As you all know, G is the gain of your antenna, and your effective aperture is nothing but A into AEFF. Okay, so this is nothing but your lambda square, which is wavelength divided by 4 pi. So in most of the questions, the wavelength will be given just like, how we saw in the previous one. The aperture efficiency was given, and the um, the size of the antenna was given, and in what frequency it's going to operate, that is also given. So most of the values will be given, just that you will have to identify the exact parameters and substitute the values. So the power delivered to a matched receiver, so PR, which means the received power, is nothing but your psi m into AFF. So we know that it is equal to EARP divided by 4 pi r square, and your this one, your effective uh, aperture is lambda square into GR divided by 4 pi. So you try to multiply both of them. Okay, so lambda divided by 4 pi, you can take it as common because you have 4 pi, so those gets multiplied. So I can put them as whole square. GR remains here as it is, and EARP is here. So EARP, GR, so these terms will actually get into the bracket. So R is the distance or range between the transmitter and the receiver antennas, and GR that you can see is the isotropic power gain of the receiving. See, whenever you see R, that is for the receiver. Okay, whenever you see T, it is for the transmitter. The subscript R is used to identify the receiving antenna. Okay, so that's what I just told. The right-hand side of the equation is separated into three terms associated with transmitter, receiver, free space, respectively. So you have your receiver, okay, and your lambda divided by 4 pi r square and EIRP, that is your free space. In now, if we have to convert to your decibel, then it becomes your EIRP plus gain minus 10 log 4 pi r divided by lambda whole square. Now, just you'll have to make note of all these formulas, and make sure as to if it's going to be in dB or the watt format. The received power in dB watt is therefore given as the sum of EIRP, okay, plus the receiver gain minus a third term which represents free space loss. So this is nothing but your free space loss. So this FSL, in short, free space loss, is given by 10 log 4 pi r square divided by lambda square. This one also you will have to remember because we will be using this formula in many such situations. Basically, it will be used for your problems. Normally, the frequency rather than wavelength will be known, and substitution lambda is equal to c by f, where c is nothing but the speed of your light and f is your frequency of operation, and that is actually in megahertz. So the distance is in kilometers, and it can be shown as, so your FSL is equal to 32.4 plus 20 log r plus 20 log f. So your f is your frequency. So we will be rewriting this received power in the form of EIRP plus gain minus FSL. So FSL, you have to substitute this value. Okay. So remembering the formulas and substituting the values is one important factor here. The received power PR will be in dBW when the EIRP is in decibel watt and FSL is in dB. So that is when you will be actually using this formula. See, that's why you see the square bracket, which I had mentioned in my previous lectures. So the equation is applicable to both uplink and downlink of satellite circuit. So which equation is that? This equation is for both uplink and downlink. Free space loss is common for both uplink and downlink of any antenna. Right. So now let us see an example, and they're asking us to find out the range between ground station and satellite. Okay, they're giving us the specification, and they're telling us to calculate the free space loss, which means FSL. Okay, so the range is given, which is in kilometers, and what is FSL? With a frequency of 6 gigahertz. So we are going to use this formula here, okay, because the distance is given, frequency is given, so this is the most appropriate formula. So I just substitute that, and I'm going to get about 200 decibels. So problems are very simple relatively, just that you'll have to find out or figure out which formula to be used, right? Similarly now, with equation 2.11, okay, so with this equation, when are we going to use? Shows that the receive power is increased by increasing the antenna gain. So as the gain is increased, the power is also increased. So that's the meaning of gain, right? So when you have input, so these signals are amplified, and if it's greater than your input, so that becomes your profit in terms of signals, and that is nothing but termed as gain. Okay, right? So gain is inversely proportional to the wavelength. So gain increases, the wavelength decreases. Hence, it might be thought that increasing the frequency of operation and therefore decreasing the wavelength would increase the received power, because gain is increasing and gain and your power is directly proportional. However, equation 12.9, okay, yeah, this which was used for both uplink and downlink. So this equation shows that free space loss is also inversely proportional to the square of the wavelength. So that's just your formula, and it follows therefore that for a constant EIRP, the received power is independent of frequency of operation, right? If the transmit power is a specified constant rather than EIRP, then the received power will increase with increasing frequency. So as we know, the power is more if the frequency of operation is higher. Okay, right. For a given dish antenna size at the transmitter and receiver, it can be shown that under these conditions, the received power is directly proportional to the square of the frequency. Okay, so you can see that here, square of the uh, values, okay, lambda. Next, feeder losses. Okay, so these feeder losses are cables which are actually connecting from one end to another end, and these losses that occur in these cables are called feeder losses. Losses which occur in the connection between the receive antenna and the receiver proper. Such losses will occur in connecting waveguides, filters, and couplers. So these are denoted as RFL. Okay, so receiver feeder loss. So RFL values are added to free space loss. Okay, so similar losses will occur in filters, couplers, waveguides connecting transmit antenna to high power amplifiers. So as as the complexity of your device increases, you can find that the number of losses are actually increasing. So you'll have to take note of this, and you'll have to make sure that even these losses are considered. If you have to model a system, then you have to model it in such a way that you take care of all these losses. However, provided that the EIRP is stated can be used without knowing the transmitter feeder losses, these are needed only when it is desired. Okay, so as I mentioned, if the losses occur, then only you will be using the formula. If not, then you will be using the previously mentioned formula, which was for the uplink and downlink. When a satellite link is established, okay, now what can cause misalignment losses? Now when the antennas are not in proper position, if they are not focusing each other, then there can be something called misalignment. So there's no proper straight line of sight between them. The ideal situation is to have earth station and satellite antennas aligned for maximum gain. So as I mentioned, your earth station as well as your satellite should be aligned in such a way that it is straight. So I'll show you the figure. Yeah. So if you consider this as your earth station and this as your satellite, they should be aligned straight. So if they are aligned straight, then there's going to be less losses. See, in the second case, what is happening, there is a slight deviation. Okay, there's a slight deviation. So because of which there is few signals that is getting scattered and lost. So satellite and earth station antennas aligned for maximum gain. So in B, it is situation on the given satellite footprint and earth station antenna which is misaligned. Okay, so your beams that are being transmitted is not in the same path. So the off-axis loss of satellite is taken into account by designing the link for operation on the actual satellite antenna contour. So we have to make sure that these antennas are facing uh, each other and they have straight line of sight. The off-axis loss at the Earth station is referred to as antenna pointing loss. So if they do not align, okay, if they are not in the same line of sight, then it becomes a loss. Antennas pointing losses are usually uh, only a few tenths of a decibel. Typical values are given in the table. I will show you which table I am mentioning about. Yeah, so this table, okay, where they have used for different locations in Canada, and they've used for uh, a particular region, okay, that is during the summer, and having a coverage of 1 by 4 and half of Canada's coverage, and how, because of these pointing losses, okay, how much that it can actually uh, suffice to. In addition to pointing losses, losses may result at the antenna from misalignment of the polarization direction. So as I told you, polarization should be the same. So if we are using a vertical polarization, the same thing should be used at the transmitter and receiver, or if it's horizontal, the same thing, or circular, the same kind of polarizations are to be used both at the transmitter and receiver. The polarization misalignment losses are usually small, and it will be assumed that the antenna misalignment losses, which is denoted by AML, include both pointing and polarization losses resulting from antenna misalignment. Okay, so what we are trying to see here is uh, due to this misalignment, there is going to be a lot of loss. Antenna misalignment losses have to be estimated from statistical data based on errors that actually was observed previously. So previously you should have some data and you should know if it's deviated by half degree, then how much of error. If it's going clockwise half degree or anti-clockwise minus half degree, then how much of variation can happen just because of this alignment. Okay, so the data based on errors actually observed for a large number of earth stations, and of course the separate antenna misalignment losses for uplink and downlink must be taken into account. So separately we have to calculate for both uplink and downlink, because that uh, these two actually contribute for your proper communication, or complete communication rather. Yeah. So we'll be looking at fixed atmospheric and ionospheric losses. So there can be losses because of the atmosphere as well. Okay, and that is given by AA90 cosec EL, which is nothing but your angle of elevation. These losses usually amount to a fraction of decibel, and subsequent calculations, the decibel value will be denoted by AA in square bracket. Values obtained for some locations in Ontario, okay, that's in Canada, is shown in 12.1. So this is your few locations that they have looked into, and how much of loss, okay, how much of atmospheric absorption that can happen, which is ranging about 0.2. The ionosphere introduces a depolarization loss, and it's given by this equation. So ionosphere also plays a very important role because that's where you find all these electrons, the charged electrons. So our beams pass through, they have to pass through this ionosphere and then hit the satellite, and then while coming down they have to pass through the ionosphere. So which means the combination of these electrons plays a very important role. So you will find a concept called ducting. Okay, ducting. So you can actually just look up, and you will find that how the rays are, you know, sent straight to the base station, keeping temperature and all these losses in mind. So your loss, okay, your loss is denoted by PL is equal to your polarization loss is equal to 20 log ECO by E. Okay, so we will look into it as to what these terms are, which is nothing but 20 log cos theta F. Okay, now we will be looking into something called link power budget equation, okay, wherein we will be exclusively seeing few formulas, as we already know what is EIRP. Now we will be calculating what are the types of losses, and GR is nothing but your gain of receiver. Okay, EIRP can be considered as input power to a transmission link. Now that the losses for the link have been identified, the power at the receiver, which is power output of the link, may be calculated. So we have to find out what is my P out. So P out is nothing but my equivalent isotropic radiated power minus losses plus gain. Why plus gain? Because it adds up to the signal. Why minus losses? Because it minuses the information signal. Decibel addition must be used. Okay, so that's why you see all are put in same units. The major source of loss in any ground satellite link is the free space spreading loss. So FSL, free space loss, is actually one of the major losses, right? So as we keep looking at these information, we can also see that these formulas are also adding up. So your equation 12.13, okay, so I have put it up directly. Yeah, this is the equation. Is the basic link power budget equation taking into account this loss only. However, the other losses must also be taken into account, and these are simply added to FSL. So if you just consider loss, there's going to be free space loss, your RFL. What is RFL? We just saw it, right? Receiver feeder loss here. Okay, your RFL. Then we also saw the atmospheric losses, AA. Okay, atmospheric loss, then polarization loss. So all these losses are adding up. Okay, and in short we call them as losses. So here you can see all the abbreviations I have put for the benefit of all of you, where PR is your received power, EIRP is in dB watts, free space loss, receiver feeder loss, your misalignment loss, atmospheric loss, polarization loss. So all these are to be taken as complete loss. So we'll just look at a small problem here, and we will try and understand as to what these are. A satellite link operating at 14 gigahertz has a receiver feeder loss of 1.5 dB and a free space loss of 207 dB. The atmospheric absorption loss is about zero point 0.5, and the antenna pointing loss is zero point 0.5. So when I say antenna pointing loss, this is going to refer to my AML, misalignment losses. Depolarization losses may be neglected. Calculate the total link loss for clear sky. So whenever they say this depolarization, that means you don't have to consider this PL. So they're directly telling don't consider PL. So my formula is going to change to FSL, RFL, AA, AML, right? So they're telling us not to consider PL. So directly you can substitute those values. Your FSL, your free space loss is 207, then your RFL is nothing but your feeder loss, which is 1.5. Then you have your atmospheric loss, right, is also 0.5. Pointing loss, okay, misalignment losses is also 0.5. So just add them up, very simple, right? So you'll have to know which parameters to add where and which factors to nullify, right? So the next important topic that we will be looking into is system noise, right? So this is also a very important topic where you will be actually only concentrating on what kind of noises and their associated formulas. It is shown in the previous sections, okay, that we saw just now, that receiver power in satellite link is very small, on the order of picowatts. This by itself would be no problem because amplification could be used to bring the signal strength up to an acceptable level. So that's why we use amplifiers, right? So if we use amplifiers, that is when we can um, increase the gain. Once the gain is increased, then it becomes very easy for us to look at the output power which is increased just because of the amplification. However, electrical noise is always present at the input, and unless the signal is significantly greater than the noise, amplification will be of no help. So if there is a lot of noise, then even though you amplify, you will be even amplifying the noises. So which means you have to make sure that your noises are as minimum as possible. So filters comes to your rescue, where you can actually look at the band pass, low pass, high pass filters, and based on the application you could use them. The major source of electrical noise is equipment, is that which arises from the random thermal motion of electrons in various resistive and active devices of the receiver. So which means we will be looking at not only the other losses, but also we are closely interested in the motion of electrons. So due to this motion of electrons, the colliding of electrons, you can find that there is heat that gets generated, and that is nothing but called uh, thermal, in short, random thermal motion of electrons. So which means there is temperature getting generated just because of this motion of electrons. So as you all know, they have their valence band, they have their Fermi level, and then their conduction band. So because of these collisions of electrons, they will move from one level to another level, and collisions actually cause this thermal factor to increase, right? So this, in case, okay, in case this happens, then what is going to happen? Resistive and active devices in the receiver. So which means they are looking, or they are monitoring at electrons in various resistive and active devices. So they're looking at the resistances, and they're looking at the active devices in the receiver. So you can just imagine that the level of complexity involved, okay, when calculating different losses. So these thermal losses is also generated in the lossy components of antennas, and thermal like noise is picked up by the antennas as radiation. So these thermal signatures are picked up as noise. So these are not needed, and these are due to the electrons. And somehow, at this point of time, we do not have much technology to work on with the electrons. So of course, we do have quantum dot cellular automata, right, which is extensively working on programming the spin of the electron, right? So that is again a booming technology wherein a lot of research is being done. So if you are interested, yes, you can look at QCDA, quantum QDC, quantum dot cellular automata, and that is a good field to look at. The available noise power from a thermal noise source is given by Pn. Okay, so noise is KTN/Bn. So where your Tn is nothing but your equivalent noise temperature. So due to temperature, it gets created like a noise signal. And then your Bn is the equivalent noise bandwidth. So B for bandwidth, N for noise, and K is nothing but your Boltzmann constant, right? 1.38 into 10 raised to minus 23 actually. Okay, so I've just missed out that. With the temperature in kelvins and bandwidth in hertz, the noise power will be in watts. As you all know, power is mentioned in watts, right? So just another 2 slides and then we will look at a small problem. The noise power bandwidth is always wider than 3 dB bandwidth. We always keep a reference with respect to 3 dB. Determined from the amplitude frequency response curve. So at one side you will have amplitude and at the other side you will have frequency. Y-axis normally would be amplitude and your x-axis will normally be frequency. The useful rule of thumb is that your noise bandwidth is equal to 1.12 times your 3 dB bandwidth, or Bn. Okay, noise of bandwidth is equal to 1.12 into B. Okay, B is nothing but your bandwidth. The bandwidth are in hertz or a multiple such as megahertz. The main characteristic of thermal noise is that it has a flat frequency. So that is the main characteristic as to how you're going to identify these thermal noises. Okay, so if it has a flat frequency, then you can say that it's a thermal noise. The noise power per unit bandwidth is a constant. So here you can find that the noise power per unit bandwidth is termed as noise power spectral density. So a very commonly used term, noise power spectral density, right? So this is denoted by your N naught. Noise power spectral density is denoted by N naught. Okay, and we get this equation which is nothing but Pn. Okay, noise power, bandwidth noise, K is your Boltzmann constant. Okay, Tn is the temperature noise, that's in joules. The noise temperature is directly related to the physical temperature of the noise source, but is not always equal to it, which is very true. The noise temperatures of various sources which are connected together can be added directly to give the total noise. In addition to these thermal noise sources, the intermodulation distortion in high power amplifiers can result in signal products which appear as noise and in fact is referred to as intermodulation noise. Okay, so this is discussed in our next section. So what we see here is we will be looking at something called intermodulation noise. So noise is not needed, and this kind of intermodulation noises are causing a lot of signal distortions which needs to be looked at. So we'll just look at a small problem here and we will try and understand as to how these are picked up and how we extract data from the problem. An antenna has a noise temperature of 35 Kelvin and 35 K and is matched into a receiver which has a noise of so much. Calculate number one, noise power density, which is your Pn. Okay, and you'll have to even calculate the noise power for bandwidth of 36 megahertz. So B is also given here. So we know that your N naught, okay, so we have this formula, your N naught is equal to 35 plus 100. So 35 is your noise temperature, 100 is also is matched into a receiver which has a noise temperature. So antenna and this one, so both I am adding into your Boltzmann constant. Yeah, okay. So once I do that, I get my N naught. So Pn, my Pn is nothing but your N naught into Bn, right? So N naught into Bn. So N naught, I have the value here. Your Bn, your bandwidth is 36 megahertz into 10 raised to 6. So I multiply both of them. So I will get about 0.67 picowatts. So I think students, we will stop here and we will probably look into the other topics, okay, in our upcoming classes, where we'll be discussing about antenna noise and how it is with respect to your frequency and the temperature, okay. And we will also be looking at the noise temperature, okay, very much important concepts. So, and how we cascade them. So all this, will be looked in our upcoming classes. So as of now, we will wind up here, okay, and uh, we will try and look at these formulas, try to make a note of them and their applications as to how you're going to use them and how you're going to extract data from the given problem and what kind of formula you're going to use and how you're going to make the best use of data and make sure that all the values are in the same unit so that it becomes easy for you to analyze. Okay, so these are some of the important things that you will have to remember, especially the losses. Losses has a lot of factors here, so you'll have to know which factor to put in and which factor to nullify, so that is actually given in your question directly. Okay, so these are some of the important things that we had discussed today. Misalignment losses, okay, the feeder losses, and we also saw a simple problem and the application of your EIRP, and totally we discussed about the transmission losses.